found that there is a serious consequence regarding the efficiency or minimum variance property of the estimator. If I estimate the parameters using OLS, both in case of heteroscedasticity as well as in case of autocorrelation, we have calculated variance beta hat, variance of beta hat, covariances of beta hat I, beta hat j. So when we calculate the covariance of beta hat I, beta hat j, we are finding that autocorrelation is creating a noise in the system. In case of heteroscedasticity, there is a problem with respect to the variance of beta hat. In case of autocorrelation, there is a problem regarding the covariances between the estimated values of the parameters. Okay. So whatever be the thing, heteroscedasticity as well as autocorrelation, it is disturbing the estimated values of the variance covariance matrix of beta hat. So we need to learn several remedial methods. As we discussed, the general terms and terminology which we will use, that is, we need to apply GLS technique, generalized least square technique, not the ordinary least square technique. Now there are different variants of GLS technique. In case of heteroscedasticity, we have talked about weighted least square technique, which is a variant of GLS. In case of autocorrelation, we will talk about Cochran or cut technique, which is another GLS, generalized least square technique. We need to learn this. What is this Cochran or cut method? Okay. So first we will talk about Cochran or cut method, and then we will identify if there is any limitation for this Cochran or cut method, and we can go for any other improved version. I hope everybody has pen and paper, because I'll tell you some steps. So remedies of serial correlation. Now first you need to check whether it is coming through impure serial correlation. It's not related to time element, but because of misspecification or omitted variable, etc. That is the functional form correct? Are you sure that there are no omitted variables? So first we need to check all these things, and you know OV test, by which you will be able to understand whether there is any omitted variable or not. You know the test by which you will be able to detect whether there is any misspecification or not. What is that test? Testing for misspecification? Anyone? In Stata? Anyone? What is the test for misspecification? Testing misspecification? Everybody forgot about this. So check all these things. You learned all these things. So, so you learned how to detect all these problems, problem of misspecification, problem of omitted variables. So if there are these kind of problems, and source of autocorrelation, heteroscedasticity are basically these kind of problems, misspecification, in that case, you have to specify the model properly, or you have to remove the omitted variable bias from the model, and then you will find that your standard errors of the regression coefficients are becoming robust. So the technique is different. If the source of autocorrelation is the omitted variable or the misspecification, after detecting these issues, you need to rectify these issues. And after that, your standard errors of the regression coefficients will be all robust coefficients, that is minimum variance unbiased estimators you are getting once you are removing this. However, if the source of autocorrelation is the time element, pure serial correlation, in that case, we will use either the generalized least square technique or new wave waste standard errors technique. We can derive new wave waste standard errors that will be also free of autocorrelation. So one by one, we will consider these methods. Now, in case of number one, generalized least square techniques, again, there are several techniques, which belong to this main category, generalized least square technique. So there is method by Cochran and Orcutt. There is method by Durbin. Okay. So there are different methods. So we will start with Cochran-Orcutt method. Now, before going to that, let's get some idea about the generalized least square technique generally we will use in case of autocorrelation. So look at the equation, regression equation. Yt is equal to beta naught plus beta 1 x1 t plus epsilon t, and epsilon t is following AR1 process. So source of autocorrelation is the time element. It is pure serial correlation. Epsilon t is equal to rho epsilon t minus 1 plus ut. So this is the structure of epsilon. This is the structure of error. Okay. So Yt can be presented as beta naught plus beta 1 x1 t plus rho epsilon t minus 1 plus ut. So what we can do, we can multiply the entire model by rho. So you are getting, and we are also considering lag by one period. We are multiplying the entire equation by rho, and we are multiplying the model by rho. So what we are getting first, if I consider one period lag, Yt minus 1 here, beta naught plus beta 1 x1 t minus 1 we are getting, plus rho epsilon t minus 2 plus ut minus 1. Okay. Or if you consider the first model, you are getting Yt minus 1 is equal to beta naught plus beta 1 x1 t minus 1 plus epsilon t minus 1. Simply you are getting this. So if you have pen and paper, you can write the equation what you are getting after using the time lag. The new equation will be Yt minus 1 is equal to beta naught plus beta 1 x1 t minus 1 plus epsilon t minus 1. Then we are multiplying that equation by rho. So it is rho Yt minus 1 plus rho beta naught plus rho beta 1 x1 t minus 1 plus rho epsilon t minus 1. So I'm multiplying equation 6 by rho and taking a lag by one period, which is giving me this kind of equation, which is given by equation number 8. I hope everybody got how we are getting equation number 8. Once I get equation number 8, I'll subtract equation number 8 from equation number 6. I'll subtract equation number 8 from equation number 6. So I'll request everybody to subtract 8 from 6 and tell me what is the equation you are getting. Subtract 8 from 6 and tell me what is the format you are getting. First, tell me about the y value, the dependent value. Anyone?
Rho into Yt minus 1 minus Yt.
I told you to subtract 8 from 6.
Yt minus rho into Yt minus 1.
Yes. Subtract 8 from 6. Yt minus rho Yt minus 1. Yes. Then is equal to subtracting 8 from 6. So what is the first term in the right hand side?
Beta naught 1 minus rho.
Beta naught into 1 minus rho. Very good. Then similarly write the second term.
Beta 1 x1t minus rho into x1t minus 1.
Hmm. So I hope everybody could do up to this. And finally the error term.
Ut minus rho into epsilon t minus 1.
So everybody is getting the error term is epsilon t minus rho epsilon t minus 1. So once you get this is the error term epsilon t minus rho epsilon t minus 1, this is nothing but equal to ut. So in the next line, keep rest of the things unchanged. In place of epsilon t minus rho epsilon t minus 1, simply write ut, where ut is the classical error. ut is the classical error. Okay, so everybody got this term. And this ut is nothing but a classical error. So once we get this kind of thing, we can present the model in this format, which is a classical model. Once I get this kind of transformation, or once I perform this kind of transformation, I'm getting a classical model because error is simply ut, which is a classical error. So equation 10 is a transformed model where the error is a classical one. Once you get this thing, you will be able to estimate these parameters, beta naught, beta 1, etc. using the least square technique because error is a classical one. So you will be able to estimate the parameters using using the least square technique, beta naught, beta 1. You will be able to estimate using least square technique. Okay. So this is the idea. So we are considering rho, the correlation factor here, and transforming the model in this format so that the autocorrelation is removed and we can come back to the classical model. So when we will learn the remedial method, number one, we need to know how to calculate this rho, how to calculate this correlation. So different econometricians or different school of econometricians suggested different techniques to calculate rho. Once you calculate the rho value, you will be able to, calculate these epsilon t minus rho epsilon t minus 1. So you will have the residual for the transformed model. Ut will be actually the et. So you will have the residual for the transformed model. Once you generate the residual of the transformed model, you will apply the least square technique to estimate the parameters of the model. So the first part in the remedy will be how to calculate rho. Once you get rho, you will generate the residual which will follow all the properties of ut, that is the classical error, and you will be able to estimate the parameters of the model easily. Okay, so put these points in your mind, the steps will be like that. Equation 10 is called the generalized least squares or quasi-differenced version of equation 6. And already we noted that the error term is not serially correlated. As a result, OLS estimation of equation 10 will be minimum variance. This is true if we know rho or if we accurately estimate rho. So this A part is true if and only if we know rho, somehow we have some knowledge about rho, or if we can accurately estimate rho. The next important point is the slope coefficient beta 1 is the same as the slope coefficient of the original serially correlated equation. Let's go back to the model. If you look at the intercept term has converted. It is no more beta naught. It is beta naught plus rho minus rho beta naught. However, we have not changed or not transformed beta 1 anyway in this method. So, interpretation of beta 1 or meaning of beta 1 that remains unchanged in the original model as well as transformed in the transformed model. So, the slope coefficient beta 1 is the same as the slope coefficient of the original serially correlated equation 6. Thus, coefficients estimated with GLS have the same meaning as those estimated with OLS. Okay. Is there any question regarding these steps or regarding the points I am mentioning here? Any question? Okay, if there is no question, look at point number 3. The dependent variable has changed compared to equation number 6. This means that the GLS is not directly comparable to the OLS. What I mentioned in the second point, the regression coefficients or the gradients, for these gradients, the meanings are same in OLS model and in the GLS model because we are not changing or transforming the gradient terms anyway. However, this does not mean we are using the same equation for the OLS technique and for the GLS technique. We have transformed the model. All yt, xt, these changed. It is no more a regression of y on x. Rather, it is a regression of yt minus rho yt minus 1 on x1t minus rho x1t minus 1. So it is altogether a different regression equation. So if these are altogether two different equations, the equations are not comparable at all. That is equation number 6 and the original equation and equation number 10 or 9, these are not comparable at all because the variables have changed. It is no more a regression of y on x like equation number 6. Rather, it is regression of yt minus rho yt minus 1 on xt minus rho xt minus 1. Okay. So both point 2 and point 3 are very, very important, The slope coefficients remain same. So the meaning of the slope coefficient across OLS and GLS will be same. However, that does not mean the two equations are comparable. So if there is any true false type question, where you are getting the R square value, multiple R square or adjusted R square value of the OLS model and multiple R square value of the GLS model. And if you find that R bar square of the equation number 6 or the OLS model is greater than that of GLS model, you cannot conclude equation number 6 is better than equation number 9. Or if you get the other way around, that is R square or R bar square of equation number 9 is greater than that of equation number 6, you cannot claim this transformed equation is giving better goodness of fit compared to the original model. Actually, the two equations are not comparable at all. Please note that the earlier equation, that is equation number 6, is called the level equation. Level equation. LEVEL, level equation. And the transformed model, we are considering the row differencing. Row differencing. We are using the row differencing method, row. Okay, row differencing method. So level versus row difference equations are not comparable. Okay, the equations are not comparable because these are altogether two different regression equations. So please keep note of this fact. Number 4, for forecasting, etc., we will use the transformed model. Okay, we will use the transformed model because in the original model there are some problems. Though the meaning of regression coefficients remain same, their variance covariances will not same between the transformed model and in the original model. In the original model, the variance covariance matrix will give you homoscedasticity along with autocorrelation. Whereas in the transformed model, you will get the standard errors which are homoscedastic and non-autocorrelated. Okay, so the quality of the estimators are changing. In the first case, you are not getting efficient estimators or best estimators. In case of transformed model, you are getting best estimators. Okay, so there are these kind of things. So if you want to go further, if you want to go for hypothesis testing, if you want to go for forecasting, naturally you need to use GLS method. Okay. Now we need to learn what are the possible GLS technique by which we can estimate rho. Possible GLS technique by which we will be able to estimate rho. Because if we can estimate a rho value, in that case, we will be able to plug these rho value in the equation of AR1 and we will get ET, okay, or estimated value of UT, or the residual we will be able to generate. And then minimizing that residual, we will be able to derive the parameters of the model. So this is very important to learn how we can calculate these rho values. So first I'm talking about Cochran-Orcutt method. I'm telling you here there are steps, However, since it will be better if you have the write-up, etc., I am telling you steps. Please write down the steps. Write down Cochran-Orcutt method is an iterative technique. I hope you understand the meaning of iteration or iteration. So repetitively, you need to estimate the values, and when it will converge, you will get no change, you will stop. Iterative method indicates that. You have to repetitively find out values, and once it converges, that is, you don't get any change, you will stop. Write down. Here we estimate the equation. Here we estimate the equation YT is equal to alpha plus beta xt plus ut by OLS and get the estimated residual ET naught. First time we are running the regression and generating ET naught. We estimate rho by summation ET naught okay. Last day we got this value of rho. Actually, you are getting this is the context, So we can try to estimate these parameters using the classical techniques so we can find out this kind of value. So last day we talked about these things. And why not UT, why we are using ET, that you know. So this is the first possible value of rho. I'm running the regression, the model we are getting, and calculating the residual and calculating rho based on the residual. So this can be considered as step 1. Okay. So this can be considered as step 1, or we can tell that this is the first value of rho hat. Okay. This is the first value of rho hat. Rho hat is equal to this. Next, then we regress yt minus these rho hat values, rho hat yt minus 1 on rho hat xt minus 1 and get the estimated residual et1 and get the estimated residual et1. So I am considering rho differencing method using the first possible value of rho, first estimated value of rho, and calculating et1. And from this step, we are calculating a value of rho, say rho hat 1 as summation et1 summation et1 et minus 1 1. Actually, we are getting the same value with respect to the new residual. Next, we regress yt minus rho 1 hat yt minus 1 on and this generates say et2. So we calculate rho hat 2 e to t, e to t minus 1 divided by summation e to t square. And keep on iterating till it converges, in terms of, till it converges in terms of RSS value, since it implies we cannot improve our explanatory power further, we cannot improve our explanatory power further by considering any other iteration. So what we are doing, first we are applying the ordinary least square to the given data set, generating residual. On the basis of that residual, calculating rho hat. Using that rho hat, we are applying the row differencing method, calculating ET1. On the basis of ET1, we are calculating next rho hat. Using that rho hat, again, we are regressing yt minus rho 1 hat yt minus 1 on xt minus rho 1 hat xt minus 1, generating ET2, calculating another rho hat. We will proceed in this way unless we find that for the last two models, the RSS values are similar. We will iterate up to, we will iterate till we get the similar RSS value across last two regression equations. If we get this, that means the system has converged. We will be not able to reduce residual sum of square further. We will be not able to improve the explanatory power of the model further. Okay, so the problem has removed. Problem of autocorrelation has removed. Okay, actually we will not do this. Software will do all these steps and give us the result, the final result. Okay, after this much iteration, we are getting the convergence. So software will give us the result and will declare the final value of rho hat. Once we get the final value of rho hat, we will stop regressing yt minus the relevant rho hat yt minus 1 on xt minus rho hat xt minus 1, and we will report these values of betas are the final values of the estimated coefficients. So this is the method, iterative method. Add one more para. However, minimization of summation et square, minimization of summation et square can produce multiple solutions for rho. Minimization of summation et square can produce multiple solutions for rho. In this case, the Cochran-Orcutt procedure, which relies on a single solution of rho, might give a local minimum, and thus while we are iterating RSS may converge to a RSS may converge to a local minimum. RSS may converge to a local minimum. Okay, so this may be the problem of Cochran-Orcutt method. Everything is perfect, however, while it's converging, etc., and we are considering the final value of rho and thereby considering the final transformation of yt to report our estimated values of the parameter, that may be based on the idea of local minimum. So there is this kind of, every method has some limitation. So there is this kind of problem. Otherwise, Fortran or cut method works good under many circumstances. Do anyone have any question regarding Fortran or cut?
Ma'am, I didn't understand the limitation.
You didn't understand the?
Limitation of this method.
Okay. What I am telling that, while we are starting with these regression equation and calculating the value of the residual, okay, and on the basis of the residual, we are calculating the rho hat value. Now, rho can be considered in a different way. Okay, I have considered et naught into et minus 1 naught divided by summation et naught square. In the denominator, you may consider et minus 1. Okay, or while you are writing this thing, since it is time dependent model, you can estimate rho not considering t and t minus 1 at period, rather you are considering say t minus 1 and t minus 2 period. You applying the similar kind of formula, but the lag is differing. So from a single residual, it is possible that you can generate a number of rho values. From a single residual in a time series analysis, varying the lag, you may generate different possible values of rho. Cochran-Orcutt is considering one particular value of rho. One particular value of rho. It is considering t and t minus 1 at period and doing the thing, because I'm considering AR1 process to begin with, and therefore we are generating this rho hat. However, AR1 process is not all in all. Your process may be AR2, your process may be AR3. So length of the lag may vary, and on the basis of that, rho value may vary. In our entire analysis, we are considering AR1 process because this is the basics of autocorrelation, or only the basic time series framework we are using. However, the length of the lag may vary, and that may generate different value of the residual, and that residual may generate different value of the rho. Okay, or you are starting with the basic construct which is identical. However, while you are calculating rho hat, you are using the different time lags. In that case also, you will get different rho value. So here we are telling that if you consider different lags and there are possible series of value of rho hat, however, you are using a particular one, in that case, this is you are talking about, or convergence of RSS you are talking about, that may be local minimum, that may not be a global minimum. Okay, so it may not be a unique minimum, universal minimum. It may be a local minimum only. Okay.
Yes, ma'am.
If you consider the AR1 process, or truly if there is AR1 process, then it is absolutely fine. However, if it may not be that so. Uh, okay, so these are the things mentioned here. The AR1 issue. So many a times we change the method. There are several methods of calculating rho. If you consider any text, you will find a number of methods. I am presenting Cochrane shortcut and the New Way West standard errors. Darby's method is also not bad. Uh, you will get Darwin's method also in many of the textbooks. So if you like, you can consider or check the Darwin's method. Remember that using these methods, basically, we are trying to find out a route by which we will be able to calculate rho value. Once we have rho in our hand, we will be able to apply the least square technique to calculate parameters of the model. Okay, so again, not all corrections for pure serial correlation involve generalized least square. New Way West standard errors take account of serial correlation by correcting the standard errors without changing the estimated coefficients. Okay, so it is more like in case of heteroscedasticity, you used the robust term, the robust command. If you use the robust command, you are running the same regression model. However, the errors you are getting, that is free of heteroscedasticity. Robust standard errors are free of heteroscedasticity. So New West method is like that. It directly changes the standard errors. It is not talking about a totally different methodology like the Cochrane or cut kind of process, that in this way you can first calculate rho and then you plug the final rho value in the transformed framework, and for that transformed framework you report beta naught, beta 1, etc. It is not doing the things in that way. So directly it is adjusting the standard errors of the regression coefficients. Okay, the logic begin. New Way West standard errors is powerful. If serial correlations does not cause bias in the estimated coefficients but does impact the standard errors, then it makes sense to adjust the estimated equation in a way that changes the standard errors but not the coefficients. Okay, so the suggestion is like that. Since in presence of autocorrelation, the estimated values of the coefficients are unbiased, so we will not disturb the coefficient values. The problem is regarding the standard error of the regression coefficients. So directly we may address the standard errors of the regression coefficients and we can remove autocorrelation problem from that. Okay, the New Way West standard errors are biased but generally more accurate than uncorrected standard errors for large samples in face of serial correlations. So standard errors, while we are considering, there is a bias in it. However, it is more accurate compared to the variance covariance matrix of beta hat if we use the ordinary least square technique. Okay. As a result, New Way West standard errors can be used for t-tests and other hypothesis tests in most samples without the errors of inference potentially caused by serial correlation. Typically, New West standard errors are larger than OLS standard errors, thus producing lower t-scores. Okay, so this is all about the New Way West standard errors because it is more related to the software kind of thing. So you have to give the appropriate command so that the standard errors are addressed, and after adjusting, as econometricians, you need to remember these standard errors may have some bias. However, the standard errors of the regression coefficients you are getting, that is more accurate compared to the ordinary least square one. So these are the two techniques I plan to talk about. There are a few more. So if anyone is interested, can check the text, etc. However, I hope you are getting some idea what will be the channel of remedial techniques in presence of autocorrelation. So this completes the syllabus of, your final examination. So I'm repeating the course once again. What are the elements there in your syllabus? Just I'm stopping the recording.